Alright, welcome to lesson 1.09. Today we're going to be talking about the intermediate value theorem and using it to solve problems. Okay, so let's go ahead and start. Alright, so to start us off, let's go ahead and take a look at this situation. The function f is graphed over to the right. It is a continuous function. And the question that I have for you is, what has to be true of f for at least one x value between 1 and 10? Or, more simply put, just what has to be true about f. Think of the first most obvious thing that comes to mind and jot it down. Alright, so most obviously, at least in my opinion, is that if a function is continuous between these two endpoints at x equals 1 and x equals 10, and on the left it's got a value of 5, and on the right it's got a value of 20, then at some point along the way, in between 1 and 10, it's going to hit every value between 5 and 20. And so for at least one x value between 1 and 10, you will be able to hit every value between 5 and 20. In other words, it will hit some value between 5 and 20 at least one time. And so this is what's called the intermediate value theorem. And so let's go ahead and now define it more rigorously without these specific values of 1 and 10 and 5 and 20. Alright, the intermediate value theorem for continuous functions. Notice, continuous functions. This isn't true of discontinuous piecewise functions. If a function f of x, and so I've graphed an example, f over here, if a function f of x is continuous on the closed interval from a to b, meaning that includes a and includes b, then for any value y sub 0 between f of a and f of b, there is a value c in this interval from a to b, such that f evaluated at c will equal this y sub 0 value. Okay, that sounds kind of ridiculous and archaic. So let's go ahead and draw an example to make this much more clear. So I have a continuous function. It's continuous on the closed interval from a to b, meaning it's defined at a and at b. And what we're saying is that for any value y sub 0 between f of a and f of b, meaning any value you pick between f of a and f of b, so let's just pick one at random. Let's call it y sub 0. For any value that you pick between f of a and f of b, you're going to have some value c that is between a and b, such that if you evaluate the function at that value c, it will get you your y sub 0 value. And to illustrate this, I'm going to show this. So we have some value that we've picked at random, y sub 0. It could be any value as long as it's in between. And notice that there's going to be some point along my continuous function that has this y sub 0 value, meaning that there will be some value in between a and b, just call it c, where if you plug that into your function, you're going to get that y value back out. Now what this means in kind of a succinct manner is that f of x, if it's continuous on this interval, is going to take on every value, every y value, between f of a and f of b. Okay? And that should just be pretty obvious, but now we have a rigorous way of defining it, and we'll see that it's actually pretty helpful. Because just think about it. If you knew that your function hit a value here, f of a, and was at another value, f of b, somewhere else, and it was continuous between those 2 points, then you know that there's going to be some place where it's going to hit every single value between f of a and f of b. So if you were looking for some specific value, you know it's going to hit that value so long as it's in between f of a and f of b. Alright, so we're going to actually use this theorem to make sense of and actually make more efficient some methods for solving equations. So let's go ahead and take a look, see how we can apply this theorem. All right, let's take a look at an example. And the face of it, this example might not seem like something that you could solve and apply the intermediate value theorem, but I think you'll find that once we go through it, it'll be pretty obvious. So what I want you to do is just give this a try, at least setting it up on your own. And to do so, at least represent this situation in an equation that we could use, that we could solve in order to figure this problem out. Okay, so is any real number exactly 1 less than its cube? And so what we're wondering, is there any real number, let's call it x, and x has to have the trait that it is equal to exactly 1 less than its cube. So its cube is x cubed, and we know that this number x is equal to its cube minus 1. Okay, so if we want to apply the intermediate value theorem, we want to have some function, and if we're trying to prove that that function is going to be equal to some value, we need to find that it's equal to a value less than that, and then a value greater than that. And so in order to make that happen, we have to manipulate this function a little bit, or this equation a little bit, so that we have a function on one side and then it's set equal to some value on the other. And the most obvious way to do this is just to move everything to one side so that you have something equals 0. That's always a good strategy to take. And so if we subtract x on both sides, what we have is an equivalent equation that I'm going to rewrite over here, which is x cubed minus x minus 1 equals 0. And what this equation is really asking us to find are the roots of this cubic function here. And so let's actually write this function out and see if we can apply the intermediate value theorem here. So this function, f of x, is x cubed minus x minus 1. Now to apply the intermediate value theorem, we need this function to be continuous on an interval. Well, we don't need an interval. This is a polynomial. This is continuous for all real numbers. Okay. So since it's continuous for all real numbers, we can apply the intermediate value theorem. In other words, if we can find some place where this function has a y value that is less than 0, and then another x value that makes the function have a y value greater than 0, then we know there's going to be somewhere in between where it has exactly a value of 0. Okay? So why don't you go ahead and find those on your own, and then we will take a look and confirm by taking a quick glance at the sketch of the graph. Okay, well, first let's find a value that makes the function less than 0. So let's just try 1, f of 1. And the reason I tried 1 is I noticed that 1 cubed is 1, and so that would leave me with positive 1, minus 1, minus 1, or in other words, minus 1. And then to find a value that makes it positive, well, I have a cube minus x minus 1. So I need to pick something that makes the cube a little bigger than everything else. So let's just pick 2. F of 2 is equal to 8 minus 2 minus 1, which is 5. Alright, so what does that mean? Well, the intermediate value theorem tells you that if you have a continuous function and you have some value a and some value b, and you know what the value is of the function at a and at b, in this case negative 1 and 5, then there is going to be some c value that will make your function equal to any value between negative 1 and 5. Meaning there's going to be some value c such that f of c is going to be equal to 0. So let's go ahead and sketch the graph quickly, and this will help us see and confirm our finding. Alright, I've sketched it very, very quickly. I recommend either using your calculator to sketch this graph out, or Wolfram Alpha to get a quick plot. And so what we can see here is a confirmation of our finding, right? When we had an x value of 1, we had a corresponding f of 1 value, or y value of negative 1. When we used 2, we got a corresponding, I'll mark those there, we got a corresponding y value, f of 2 at 5. 5 and negative 1. Okay? And so that means there's going to be some place along our function in between 1 and 2 where our function is going to hit 0. And that place is what we call c. Right? There's going to be some c value such that f of c is equal to, in this case, 0. Okay? So what I would like you to do is go ahead and write up your final answer. Make sure you're including all the key pieces and talking about how you include the intermediate value theorem. We'll compare our written up answers in class, and I will give you a couple of more problems that are sort of similar to this that you can apply the intermediate value theorem and should apply the intermediate value theorem to solve. Alright, so here are 3 different questions for you to try. Notice that the second one is from your book, so you can go and check your solutions to that to ensure that you've gotten it correct. And just a fair warning here, you should use the intermediate value theorem to support your answer, and you should write out your answer in, kind of paragraph, not kind of, but in paragraph form, and talk about how the intermediate value theorem proves that your answer is correct. Alright, so give each of these a good try. If you need to, go back and look at your notes to kind of refresh your memory and help you apply the theorem correctly.